All right. Hello, everyone. Welcome back to another week of the Experimental Math Seminar. This week we have Paul Ellis, who's going to speak to us about the arithmetic periodicity of the combinatorial game cut.
Thanks, Robert. And thanks, Garon, for inviting me, and thank you everyone for coming. I'm going to assume that no one knows anything about combinatorial games, and I'll just say a couple things to introduce the topic. This is, of course, a joint work with Ake, Tatsapan Tanati Panon. He goes by Ake. He and I were both students here at Rutgers a while back together. So we start with just what I mean by a game. A game can mean many different things, but today what I mean by a combinatorial game is a two-player sequential loop-free game with perfect information. So I mean that both players can see everything that's going on. There's no loops, so it does terminate. It's sequential, the two players take turns. That's basically it. Also, furthermore, these other two conditions, there's a lot of theory when these two conditions are negated, so I've made them separate. But the kind that I'm most interested in is impartial games, which means that both players have access to the same options. So an option is which moves you can make from the current position, let's say. And so chess is not impartial because white can only move the white pieces. Yeah. Nim is impartial. Nim is the quintessential impartial game. This game is also, all of our games that I study are normal play, which means the player who makes the last legal move wins. Which is the same as saying if it's your turn and you have no legal moves, you lose. Okay. The opposite of normal play is misere play, which has a lot of interesting theory. In the partial games where players have different options also has a lot of interesting theory, but there's quite a bit going on just with these restrictions here. So any questions about kind of where we're at so far? All right. Let me give an example. This is the first example. I've taught this to very small children, and I think it's a great teaching game, actually. It's takeaway 1, 2, 3. The setup is there's a pile of tokens on the table, and the options are that you can remove 1, 2, or 3 tokens from the pile. Well, remember, we're playing normal play, which means you want to be the one to take the last token off the table. Okay. And this is also to introduce kind of the vocabulary. A position is a winning position if the player whose turn it is can guarantee a win, and it's a losing position if they can't, if the other player can. In this example, we can classify all the positions with a chart. Now, my chart should go off to infinity, of course, but I only have so much space. So what then? How does this chart fill in? Where's the winning positions? Where's the losing positions? Give you a second to think about it. Or maybe I should ask.
What about you say?
No, Paul, please. I will.
Well, zero win or lost. Zero when it's your turn. Have you won or have you lost?
I guess no one's played anything, right?
Yeah, but I've played something and now it's zero and it's your turn.
Oh, then you lose, right?
That means you've lost, right? But what if it's 1? Can you win, Robert?
I could take away 1.
Yeah. Can you win if it's 2?
I can take away 2.
Can you win if it's 3?
I can take away 3.
Can you win if it's 4?
No.
Why not? Because whatever you do, I'll take the compliment, right?
Right.
Ah, okay. And how about 5, 6, 7? Can you win?
With 5, you can take 1 and get down to 4, for example.
And 6?
You can take 2 and get down to 4.
And 7?
7, you can take 3.
How about 8?
No.
Because I can make it 4, right?
Yeah.
Okay,
Pattern's going to repeat after this.
Exactly. So multiples of 4 is the losing positions. You can see that that in this version of the question, the positions that are interesting are the losing positions, right? Because here this has this interesting description, the multiples of 4, and it sort of describes the strategy, right? They're the ones you want to make it. Like if it's your turn, you want to make it into a multiple of 4. So that's describing the winning strategy. That's one way of looking at these combinatorial games. That's not the one we're interested in, unfortunately.
Paul, I used to play this game with my little kids when they were 4-year-olds.
Absolutely.
And they really liked it. But once they became 5, it stopped being fun.
I taught a summer camp in Beijing, and the kids were like 1st, 2nd grade, and I was teaching this. It's totally doable. You can totally play, and variations. There's all kinds of variations on this also. This is not the point of view we actually are interested most in. What I care more about is these nim values. Okay, so we can recursively define the nim values. I'm going to call it g of n of a position n. And what it is, it's going to be the MEX. MEX is short for minimal excluded value of the values of its options. So for example, when I say MEX of like the multi-set 0, 3, 3, 1, 5, I mean the smallest natural number you don't see. Okay, minimal excluded natural number value. So 2 here. So we start with 0 being 0. Okay, and then look at the options that you get from 1. From 1, what the only option is 0. And so if the MEX of that, the MEX of just the set 0 is 1. And if we look at 2, its options are 0 and 1, so the MEX of that is 2. If we look at 3, the MEX of that is the set 0, the options are 0, 1, and 2. And those nim values are 0, 1, and 2. So the MEX of these nim values is 3. But then if we have 4 tokens, the options are here. They're 1, 2, and 3. And then the values you see here of its options are 1, 2, and 3. So what's the MEX of 1, 2, and 3, Robert, going to be?
0.
Right. Now, can you guess the significance of 0?
So these are probably the losing positions.
Probably. Yeah. So the 0 are the losing positions, and the winning positions have positive nim values. Exactly. And so this is going to be, again, 1, 2, you can kind of check, it's 1, 2, 3, excuse my handwriting, 0, etc. And you can see that for 5, the options have these nim values, so the MEX is 1. For 6, the options have these nim values, the MEX is 2, you know, and then for 6, it's up 7, it's up to 3 again. So you get patterns like this. And it's kind of counting the number of steps away from a losing position. It's actually an ordinal number of steps away. You're actually literally doing a sort of ordinal count. But for today, I can just tell you it's that. And then there's one other rule for computing these that's going to be important, which we'll see. Is it cool, Robert, if I go in and describe the game I actually want to talk about now?
Sure, please go ahead.
So our game is called Cut. Now, Cut, the setup is there's many finite piles on the table. So instead of one pile, there's multiple piles. The options are that, well, first of all, each version of Cut is specified by a cut set. The cut set is a subset of the naturals, all right? And then an option, what you're allowed to do, an allowed move, is to select one of the piles and some element of the cut set, and then replace the given pile with a partition into d+1 parts. Please note, the total number of tokens does not change in the whole game. So I'm going to take a pile of size 10. If 3 is in my cut set, then I'm going to take that pile of size 10 and split it up into 5, 2, 1, 2. I have to think about. Yeah, so that's an allowable move. And I get more piles, same total number of tokens. But because the partition has to be a proper partition and a non-empty sets, this terminates. For example, if all of the piles of size 1, this would be terminated.
So the tiles are identical. It's just the number, and only the number on each pile counts, right? Matters.
I'm sorry, say it again?
The tiles are indistinguishable, like pennies.
Oh, yes, yes. Right, the tokens are indistinguishable, absolutely.
And I also get to pick the size of the parts of the partition?
Yes, yes. The only restriction is how many parts in the partition.
Okay.
So the input is really a list of integers.
Right.
A set of integers.
Yeah, it's a multi-set or whatever. Yeah.
Yeah,
Yeah.
multi-set of integers. Okay. Positive, yeah.
This naturally asks the question, then how do you calculate nim values when you have multiple piles, right? Because notice this is the MEX of the various options, but what if your option is multiple piles, right? If it's a terminated pile, it's 0, right? Because that's kind of the base case is the 0.
And so sorry, Paul, I don't understand the rules. So in usual nim, you have a number of piles, 3 or more, but 2 or more, and the legal move is removing any number of tokens or pennies from it. So say again, what is the rules of the game? What's the legal move? I didn't get it.
Right. So the legal move is to select one of the piles and one of the numbers in the cut set, right? Because we need to pick one of the rules that are in the rule set. So the C is like,
the cut set is given, it's part of the game.
yeah, it's part of the game. A version of cut is specified by this rule set
Okay.
called the cut set. What you do is you replace the pile with a partition of it into D+1 parts.
Okay, but
So can you give an example of can you give a simple example of a legal move?
Oh, yeah. So, absolutely. So let's say that C equals, just say 2, 3. Okay. If I have a pile of size 5, I can, and let's say a pile of size 2, I can't actually select this pile because I would need to split it into either 3 piles or 4 piles. Because, but I can't split into 3 or 4 piles, but this one I could. So what I could do is I could leave the pile of 2 alone, and I could split this pile into 3 piles. They have to be non-empty, but it's my choice how. So maybe I'll do 2, 2, and 1. And now the new position is here. This is the new position. It's 2, 2, 2, 1.
Thank you.
Sure.
Okay, but a question. Is it the last person to have a legal move wins or loses?
Wins.
Okay.
Yeah, that's the normal play. If you do Misere play, which is the opposite, then instead of having integer values for your nim values, you have to use the surreal numbers at some point. So we don't do that, or at least I don't yet.
Yeah.
It's my understanding that's how Conway came up with them, was actually motivated by Misere play games, but I'm not sure if that's entirely accurate. Okay, so there's another rule which we're gonna have to take on faith today because otherwise I'm spending time on that theorem's proof, but the kind of fundamental theorem is this thing called the Sprague-Grundy theorem. The Sprague-Grundy theorem says that for any disjunctive game, now cut is disjunctive, and that means that every move only affects one of the piles at a time. In other words, if I have piles here and piles here, the game position that's both of those piles together, one move only affects one of those parts, right? It doesn't affect kind of all of it simultaneously. It affects one of the parts, one of the piles. Then you add, to get the nim value for the whole position, you add together the values of the piles using what's called the nim sum, and this is binary sum modulo 2. So if you have a pile with value 9 and a pile with value 11, convert those to binary, then sum the digits without carryover. So then 1001 plus 1011 would be 0010, or the value 2. So it's binary carryless addition.
So this is XOR, right?
Yeah, XOR, right. And where might you have seen this before is the solution to nim. This is why nim is the foundation for these, and why these are called nim values and nim sums and all this stuff. Yeah. Okay, so that's what we're going to do when there's more than one pile. We're going to recursively define the values of multiple piles this way. But even this also helps us define the value of a single pile, right? Because you have to define it based on the mex of all of its options, but each one of its options is multiple piles, right? Once if you have a pile of size 10, a move is splitting up into more than one pile. So you have to do the mex. So that one option has a value, but to find that one value, you have to use this nim sum on the individual numbers there. Okay.
Then isn't it the case that if you have a non-zero nim value, then you have a winning position because your move always reduces it to 0?
Yeah. Well, yes. Yeah. That is true.
So you're going to show us how to do that.
Well, not exactly. That's contained in the proof of the Sprague-Grundy theorem. Right now, our goal is to compute these nim values because they're interesting sequences.
Okay.
We're going to talk about these nim sequences. So the thing is, because of this, because there's a way to do this, we've got the whole set of nim values if we just find the nim values of the single pile positions, right? Because if we have more than one pile, we can use the nim sum to add them together. So this is actually our goal here. Our goal is to look for the sequence of nim values on all the different single pile positions. And that's going to be true for any such normal value invariant, normal value impartial game, not just cut. So long as it has this kind of disjunctive quality, this is all we really look for, and the rest is sort of implied by, well, you could compute any other. So it's like computing just the atoms. All right. As a warm-up, I want to first say cut was defined pretty darn recently, which I still think is strange, because though it's not like NIM, it's partition game instead of a subtraction game. NIM, you take tokens away. Here we just kind of move them around and re-partition, but it was still only a couple of years ago. So the paper that Ake and I built off of is this one by Daly, Duchenne, Larson in Paris from 2020. They defined cut. They have some examples, and let's do one together. Suppose that you have the element 1 in your cut set, and other than that, your cut set only contains odd numbers. And the cut set can be infinite, so the rule set can have infinitely many types of options. Let's figure out the NIM sequence here. This is called the NIM sequence now, this GN. Well, for 0, it's 0. That's for sure. And for 1, well, I can't really split it into anything, right? So it's also 0. It's a terminal position. In fact, for cut, we're really going to start at 1, because 1 is always terminal anyways. You can't split 1 up into anything. And then what about 2? If you have 2 tokens, what can you do? Robert, what are the options here?
I can only pick the 1 pile and split it into 1 and 1.
You can split it into 1 and 1, and each of those has NIM value 0, and 0 plus 0 is 0, right? So what's the mex of that? What's the mex of just 0?
1.
Right. Huh. Now, what if you have 3, Robert? If you have 3, you can split it into 2 piles. Remember, so I'm sorry, this is their notation, but a number being in the cut set means you split it into p plus 1 piles, and
Right.
it's like you're making this many cuts. That's why they.
So I can do 2 and 1, or I can do 3 1s.
I can't do.
It's not possible. Yeah, never mind.
You do 2 and 1. Well, 2 and 1 has the value 0 nim sum 1, which is 1. Okay, and what's the mex of just 1 alone?
0.
Mex of that is just 0. Now suppose you have 4. If you have 4 tokens, you can split it up into 2 piles, or maybe into 4 piles. Maybe into 4 if 3 is in here, because it contains odd numbers, right? So if you split it into 4 piles, you get a bunch of 1s, which is 0, right? But what if you split it up into 2 piles? Well, it's either 3 and 1, which is 0 plus 0, or it's 2 and 2.
Which is also 0, right? Because it's
also 0 because of this guy, right? So either way, the value of an option is 0. So what's the mex of all those zeros?
it'll be 1.
Guess what the sequence is.
0, 1, 0, 1, 0, 1.
Yeah, it is 0, 1. I'll leave it as a bit of an exercise. But it is 0, 1. It's a parity kind of thing happening here. Because recursively, if it's all odd piles, or if it's all even, you're going to get 0, and if there's an odd and an even, you're going to get a 1. So yeah, that works out. Here's the next proposition. If cut contains the values 1, 2, and 3, if the cut set contains 1, 2, and 3, then the sequence is n minus 1. Now, I don't want to show the whole proof, but I want to show a bit of how this kind of thing goes. So I copied down this chart from their paper. So let me just show kind of how this sort of thing goes, which is that for a given n and a given g less than n minus 1, because we're trying to prove that a pile of size n has nim value n minus 1, right? Okay. That means we want to show that when we mex, or the set that we're taking the mex of contains all the numbers less than n minus 1, but not n minus 1. I'm going to leave that half out. That half I'm leaving out just for brevity. But we do want to show it contains all the numbers less than n minus 1. And how do we do that? We have to construct options that have those values. So they've done that here in this chart. Okay, and again, not my chart, right? So if n is odd and the smaller number g is also odd, then this option into 4 pieces. And why am I allowed to do 4 pieces? Because 3 is in the cut set. Adds up to n and has value. Let's see, these 2 cancel. That's 0. This one has value 0. And this has value, by induction, g. If g is even and n is odd, you kind of do the same thing. But what you needed was that 2 was in the cut set. So you're allowed to split into 3 pieces instead of 4 pieces. And so I hope you see how this kind of, you could like cleverly looking for the options that have the values you're trying to find to show that the max value is at least this because it contains all the previous ones. That's how parts of these proofs often go. The sort of clever choice of different options. Okay, and then here's the next proposition, which I'm not going to talk about the proof of, but just to see what kind of sequences appeared. If the cut set is 1, 3, 2k for some k, then the nim sequence, it turns out, is 0, 1, 0, 1, 0, 1 k times with a jump of 2. And this is the arithmetic periodic notation. What it means is this. It means you repeat 0, 1 k times, then you add 2, which is 2, 3. So add 2 to each part, and you get 2, 3 k times. Then you add 2 again, which is 4, 5. Then you add 4, 5 k times. Then it's going to be 6, 7 k times, etc. And that's the name of the sequence. So this is it's called arithmetic periodic. It's periodic, but the periods you jump a value every period. You kind of add this constant value every period. Okay. So just to see what kind of sequences there are and how complex this can get. And then another proposition is that if the cut set is 1, 2c, where c is either 2, 3, 4, or 5, this is the nim sequence, which is a big monster of a weird thing, right? It's this complex mess. It's 0, 1 c times, 2, 3 c times, a 1, then a 4, then 5, 4 c minus 1 times, then 3, 2 c times, then 4, 5 c times, then 6, 7 c times. But that's just the first period. Add 8 and do it all again. In fact, it looks like this. This is the first period. It has length 12c, which we can think of as 6 rows, each of with length 2c, with this strange anomalous 1 right here. And they proved this for c is 2, 3, 4, 5, and the cut set is 1, 2c.
Paul, this is due to the original people.
Yes, DDLP is the original, yeah.
And the game cut was invented by these people?
Yeah, as far as we can tell, that was the first time it was ever mentioned.
So it's a new game. Okay.
I know, and I think it's very strange because the rule set's pretty simple. It's just like partition according to some set rule of partitioning.
So right now you're reviewing what they did, and you're gonna tell the new stuff later.
The new stuff is right here.
Okay. Thank you. Thank you.
Yeah. The deal is we prove it's true for any C here.
And did they make a conjecture that you proved, or you just came up?
What's that?
Did you answer a conjecture? Did they raise the questions?
Yeah. I mean, they saw it was true for 2, 3, 4, and 5. But naturally, they would think it's true for any C. It was in their paper, yeah.
There was officially a conjecture that you proved.
Yeah, it was open question 1 or something in their paper.
Oh, okay, thank you.
Yeah.
Nice.
So Ake found this, I'll be honest, Ake found this, and he used his computer to find it. And then he brought me on to help kind of fill in some gaps in the proof. So the proof is long, okay? I'm just gonna say the proof is long, but I hope to show you Ake's insight about analyzing some NIM sets, because he did some really interesting calculations. I mean, like, it's not like his code was interesting, but what he found, some of the patterns he found to discover the proof of this were quite interesting. And this is why it's experimental math. So again, this is the first period of the sequence, like this. And the dots are so that each row here is length 2c and the whole period is then 12c. And that's the NIM sequence for this game, 1, 2c for c is at least 2. Okay, I want to talk about these nim sets. It's the nim set is kind of the natural definition. All right. If you're going to start analyzing this game, you're going to notice that the game is the cut set is 1, 2C, right? So there's two types of options. There's splitting into 2 piles or splitting into 2C plus 1 piles. And so it makes sense naturally, I think, to analyze those separately. What happens if you split into 2 piles these ways or to 2C plus 1 piles that way? Sure, let's compute. So the nim set capital N NPC is the cut set, the size of the starting pile, and then P here is the number of piles we split into. So for cut set 1/6, you're going to split it either into 2 piles or 7 piles. Okay, and then the values you get here are then calculated according to the game itself. So recursively, this is just the first step, and then recursively you build off whatever else happens in the game after that. Okay, so you'll see you get these sequences of nim sets. So nim set for cutting to 2 piles with 1/6 is like, well, empty, then 0, 1, then 0, 1, then 0, 1, then it becomes 0, 2 here at 8, 1, 3 at 9. And for splitting to 7 piles, you actually can't do anything until you have 7. Then you can split it into more piles. It's actually empty for 1 through 6. And here's what the data starts to look like. Okay, and then from those, you mex the whole thing, right? So the mex of 1 and 0 here is 2. That'll give you the nim value for 7. The nim value for 10, for example, is the mex of 0, 1, and 2, because those are the nim values of all the different options. Okay, then all the different options for 17 have nim values 0, 1, 3, 4, 0, and 2. So the mex of that is 5. Okay. Now, of course, the nim sequences for, let's say, 1/8 is going to be some kind of shift expand version of the nim sequences for 1/6, right? Like it is. It's just like the dots are longer, right? Should be the same nim values, but that means you should expect a correspondence between the nim sets also. So these sets here, you would expect a similar correspondence. Kinda. Here's what I think is the surprising part. I don't think it's exactly the way you'd expect it, because let's look at the nim values for the game 1/6, sorry, the nim sets for the game 1/6 and the game 1/8. If you look at the bolded thing, you do get a kind of shift expand thing happening here. Like you get this repeat and then the repeat, oh, that should be bold, sorry, this one should be bolded. But like this 0, 2, 1, 3 is like repeated here. So it makes it longer by 2 units in each row. But I want you to see what's surprising. What's surprising is this 3 and this 3. You'll notice that the 3 here, splitting into 3 sets, is not part of the game. This game, you're allowed to split into 2 sets or into 7 sets. This one, you're allowed to split into 2 sets or into 9 sets. But these nim sets have this correspondence even for the p-values that aren't part of the game. Even though recursively, the way these individual numbers are calculated are according to the rules of the game. But this first step, it's as if you're playing a different game. And yet there's still this correspondence. And it turns out we need that. We actually needed that. So p equals 3 corresponds to like as if 2 was in the nim set, and it's not for either game. In fact, this holds for all p. This correspondence, and Ake noticed that you need an induction that uses all the different p values, including all of the p's that aren't in the game, because the game only really uses 2 different p values, but we have to calculate these sequences kind of for all p and show an induction that uses all of them. And there's no way I would have found that without a computer. Absolutely not.
But the final proof is human readable.
Yeah.
It was inspired by computer experimentations.
Right. These correspondences were found, but then Ake said, look, I found some correspondences, but there's a lot of details. Can you help? And I said, perfect. It looks really cool. Let's do it.
I know, but it would be even nice if the computer can do everything by itself. Also.
That would be. I This is the limits of my ignorance, though.
Okay. Okay.
So stranger yet, the key ingredient of the proof is this lemma. This lemma says that the nim sets have this correspondence. And if you look, the nim set for n plus 1, splitting up into p plus 1 positions, is equal to the nim set for the same game, splitting n into p positions. Both of these p's might be irrelevant to the game. So this is actually one of the key lemmas, and it just seems to come out of nowhere. No way to discover this without lots of data, you know? It took us a while to write the proof, because why do these patterns hold? They're very counterintuitive patterns actually in the middle of the proof, but we needed them to get to the final induction.
That's a proof is by induction, right?
It's by a multi-layered induction. It's actually kind of hairy in the middle.
Ah.
You got to do it. Yeah. You know, Ake was like, I wish this could be nice. And I said, me too, but I think you got to go through awful steps to get it down. So that's probably all we have time for, more or less. But I do want to say that this lemma actually helps us prove a corollary. And it's pretty short. So the correspondence between nim sets let us prove this corollary, which is that if we start with our original theorem, which is here, that we calculate the nim sequence for this cut set, which was the conjecture, right? The conjecture of the DDLP. Then it actually has the same nim sequence as this one, if you add a few more even numbers afterwards. And it can even be infinite. So it has the same nim set as just the initial two cut sets, because of the initial two values. It has the exact same nim sequence. And the proof, the key step in the proof is here, which is that the nim set for n comma p plus 2 comma for a game, you can subtract 2 from both of these and get back down to p. And there's an exercise, sorry, it's another one of our lemmas, that adding 2 to this just makes the nim set possibly bigger. And so you get this equivalence here, that this is contained in here. So in other words, when you mix together all these values, all the different options for this infinite set, so you can split into 2 piles or any one of these odd piles, all of these, so by induction, it's the same as for this game as it is for this game, once you split it down into the nim values here. But then by this star here, all of these for the larger even numbers are contained in the one for the smallest even number. And that's because of that strange lemma. And so actually the nim sequences are equal. So first of all, any questions? I know this last part's a bit heavy in the notation. Yeah,
did you implement it in a computer? So if you have many parallel games, you can teach, you can implement it. So you have an algorithm to find the exact Sprague-Grundrisse or the nim values.
Yeah.
So I was curious if you actually
Its website has all the maple code.
Yeah, indeed.
Of course.
Yeah.
So would you like to see, I have a tab if time, just because there's some other stuff, other patterns we found with the computer that I think we wouldn't have found without it. Or go to open questions and bibliography.
Well, we have more time, so whatever you want.
Yeah. So let me just go to this set of observations. If we look at the first 30 nim sets for C equals 1 set and P equals 2. So these are those nim sets where you split into 2 piles first, and what set of nim values do you get? And this is just for the game 1-6. I wrote them here, but I wrote them in this kind of like horizontal order where you get these alternating subsequences. So the yellow sequence starts here and then just sort of ends here. So when you have a pile of size 12, this 0 just kind of leaves the sequence. And then for this blue sequence comes in when n equals 8, but leaves here at n equals 18. And these subsequences, they all begin at very specific numbers. I'll say which numbers they are. They're the numbers that are the beginning of these rows: 1, 7, 13, sorry, 1 mod 2C, but also this. So if you count this as a row separate from this individual entry, then they start at the beginnings at partitions whose values are all from the beginnings of those rows. And they exit at partitions whose values are all from the ends of those rows. And again, that's very much a computer generated kind of observation. You know, which options give you those values? I mean, it's often it's more than one, but they all have that in common. Like here, this blue one here at 20, this 3 comes from either this option 13.7 or this one 19.1, but 13.7, 19, and 1 are all 1 mod 2C. And so they're all those kind of entering numbers. And we called those in numbers, the beginnings of the rows, and the ends of the rows out numbers. We called the partition entering or exiting if it just had those kind of numerical values. And it turned out looking at those was such a key thing. Furthermore, these two propositions were very much by observation with a lot of data that if P is greater than or equal to 4, then the exiting partitions don't ever really exit. They can be replaced with the non-exiting partition with the same nim value and the same size, same n here. And an entering partition, if it doesn't have a part of size literally 1, then it can be replaced with a non-entering partition. So it told us where these subsequences were, like it narrowed down where they began and end, and that was a key thing for this expansion thing we had to prove, right? But without like being able to kind of dig into which partitions give you this or this, which we need to generate a lot of data to find all of the right patterns, exactly how they work, it wouldn't have worked out so nicely. Yeah, so I had another observation. This one, yeah, I mean these were just useful decompositions, but if you're trying to understand how these nim sums work, this was just, maybe it's not so interesting today, I think. So maybe just the open questions. One observation that DDLP found that we used quite a lot was that because the jump is a power of 2 and it's greater than all the nim values in the first period, so our jump is 8, like it jumps by 8, then essentially there's this like division algorithm style thing where you only need to look at that first period for a lot of the analysis. It turns out that a lot of it is just like, well, you're adding a multiple of the saltus at some point, so you're only looking at kind of the remainder for a lot of calculations. That's really, really useful. And the proof is kind of like, kind of like the division algorithm in spirit. Okay, so just the cases that are left, they proved what the nim sequences are for various cut sets. We proved the cut set, this one is this one, or even if you add more even numbers after the initial C. And these are the families that are left. If you have 1,3 with a bunch of more even numbers, or 1,3 with some evens and some odds, it seems like it's 0, 1, 0, 1 with a jump of 2. If it's 1 with more evens and odds greater than 3, then it looks like, well, we're not sure. We're not exactly sure. And if it's if it contains 1 and 2 but not 3, still not sure, but it does seem ultimately arithmetic periodic. And then if the game is exactly cut set 1, 2, we have no idea, and it just seems completely anomalous. So there's a lot of room for improvement here. There's a lot of cases where we're not sure what's going on.
So you couldn't find any patterns for these conjectures yet?
No.
Interesting.
I mean, the first two were, I'm not even, they're not really even our conjectures, but so this first one, it just does seem computationally to be this, right? But we don't have a proof yet. I think this one's the easiest one to work on, is this first one.
So you're currently trying to prove it?
No, we're working on something else with Andrew, actually, to do with games that are defined using like number, what do you call them? The number theoretic operations like quotient function and divisor and such.
So other people are welcome to try them. Okay.
Yeah. Absolutely. be happy to help you work on it. Help you to see what we can find. And then if you're interested in games but know anything about it, these two books are pretty good. This is the foundational book that everyone reads, which is by Berlekamp, Conway, and Guy, Winning Ways Through Mathematical Plays. It's a 4-volume set. It's an amazing set of books that's very hard to read. And this book is a bit easier to read, a little bit more recently. And then this was the paper we referred to, and this one's ours. And I should have put this in the chat. I'm really sorry. I meant to put this in the chat in case I went too fast. Oh, well, maybe I can't paste in the chat. Continue many sequences realizable this way. Oh, Brian, of course you'd ask that. Brian's a set theorist. I don't know. Well, the last conjecture, suppose, implies possibly, right?
Well, no, the last conjecture says, if you have ultimately arithmetic sequences, there's only countably many of
Oh,
those.
sorry. The last open family is like, I don't even know what this is. So could be irrational,
Mhm.
In fact, one of the most famous games is something called Grundy's game, which the NIM sequence, it just doesn't seem to have any pattern at all. It seems to be some irrational business. And Grundy's game, I'm gonna hold on. Let me just have it right here. I want to misquote a rule set, but it's the one where you're allowed to split. You can partition any pile into 2 smaller piles of unequal size. So it's a partition game. You can take any pile that's greater than 2, and you're allowed to break it apart into 2 piles of unequal size. That's the only rule. It's kind of like cut, a partition game, but the sequence for that is completely unknown. You can Google like the first, I don't know, million values or something. It's posted somewhere public, but there seem to be these irrational sequences.
So is this sequence in OIS at the beginning?
What's that?
Is this sequence as the OEIS?
Grundy's game is on OEIS, yeah. I don't know if these cut ones are. How do we submit that? Someone here.
Are you sure?
Okay. I will.
So is your talk finished?
Yeah, that's it. Sorry.
Oh, so let's thank Paul for a great talk. Are there any questions?
I guess we already had one, but
So I have a general question. So Ake found lots of patterns on the computer and conjectured a general, and you came along and you proved them by induction.
I mean, he had the key lemmas essentially in place, but it turns out the needed induction was a little more subtle than just putting the lemmas in the right order. You had to really weave them together in a very particular way. It looked like, and he wasn't wrong to think this, that there was this, that there was this like correspondence. You could just say this set goes here and this set goes there, but it didn't work out so nice. So we had some gaps to fill. Yeah. He saw that I had written a chapter for a recreational math book about math circles that was how to teach NIM. And he said, oh, then maybe you want to help me with this NIM project, this game project. And he said, read chapter 4 of Winning Ways, then come back to me. And I did. So it was good.
Good.
And I've had a lot of fun getting into this field. It's really interesting, I think.
Yeah, really fun.
and Paul, your paper with Ake, it's not online somewhere where we can see it.
It
yet,
is.
right?
It's here.
Okay, there it is.
Yeah, this one. Sorry, I thought this was a clever way of writing the bibliography. Maybe it's too clever.
That's good. Well, there are no more questions, so thanks so much for coming. And in 1 week, we have a great talk by Yakov Malinovsky. We hope to see you there.
2 weeks, right? 2 weeks.
And no, in 1 week. Because
2 weeks is Thanksgiving.
Oh, we moved it. Okay.
In 1 week, because Thanksgiving.
Okay, good.
Yeah, normally. So I hope to see you there. Okay, so Robert, please stop the meeting. Thanks so much for coming, and thanks for a great talk, Paul.
Thank you.
Bye-bye.
Thank you.
Thank you.